will introduce our next who is going to talk on high surface area acidic oxides of niobium alumina, and the main author is called Carnegie Mellon University.
In the last couple of years, we have been interested in the acidic properties of multi-component oxides. And this morning, I would like to talk about the system consisting of niobium and alumina. And I would like to start by presenting some results on the preparation of bulk mixed oxides consisting of these two components, which was prepared by a standard co-precipitation technique. The precursor which we used in this case were niobium ethoxide and aluminum nitrate in a methanol solution. Ammonium hydroxide was then added to this solution to co-precipitate the mixed hydroxides, which was then washed repeatedly and filtered with deionized water. The cake was then baked in an oven at 380 K as an initial drying step, and then we have used two calcination procedures shown below. The first one, which I will refer to as our low temperature calcination throughout the talk, is one in which the sample was heated in nitrogen at about 673 K for 2 hours, followed by heating in oxygen at 773 K for 2 hours. We have also treated our samples, which what I will refer to as a high temperature treatment, which involves taking one of the samples pre-release calcine at a low temperature by ramping it in helium to basically 1,000 degrees C at a rate of 10 degrees C per minute. Instead of showing you actual data, in the interest of time, I will just summarize the result for these series of mixed oxides in words. We have, by adjusting the amount of precursor used in the solution, prepare a series of oxides ranging from pure alumina to pure niobium, and three intermediate compositions shown here by the two numbers in the parentheses representing mole percent. So a Na5050 sample is a niobium alumina mixed oxide containing 50 mole percent niobium and 59 mole percent alumina. The BET surface areas of these materials cover a wide range, and in fact, as a general rule, the surface area decreases with increasing niobium content. So the pure alumina has the high surface area, whereas the pure niobium has the lower surface area. Now, as to be expected from such a preparation, these mixed oxides all exhibited acid strength as determined by Hammond indicator. Furthermore, they all show acidic properties in the sense that they are capable of absorbing a base, and in this case is determined by titration with N-butylamine, and they all catalyze the acid catalyzed reactions of 1-butene isomerization. Basically, you take 1-butene and make cis or trans 2-butene from it. Another feature of these mixed oxides is that after the low temperature calcination, they are all X-ray amorphous, and this particular sample is the 25-75% mixed oxide, as calcine has a surface area of about 260 meters squared per gram. But after the high temperature calcination, notice the emergence of new diffraction features, and concurrent with that, a significant loss in the surface area, in this case roughly by a factor of 3, from 260 meters squared per gram to about 80. Indexing of this peak show us that with this high temperature treatment, we were forming now a niobium alumina oxygen compound of stoichiometry NBALO4. Now, when that happened, we also observed a significant decrease in acidity. This is one of several slides which I'm going to show, in which we are plotting the acidity in terms of millimoles of base and salt. Again, is a standard titration, normalized by the surface area of the support, plotted as a function of pKa range. In this study, 6 indicators were used, and the amount of acidity over a particular range is shown by the bracket or the 2 indicators before and after that. First, I want to draw your attention to the field boxes which represent the acidity distribution after the low temperature calcination. And this is the first time I show you the actual data. In fact, you can put a lot of base on this sample, meaning that it's an acidic surface. And in fact, most of the acid sites show up at the pKa range, which is less than minus 8.2. The way that you read this figure is when you go to the left, it's more strongly acidic in terms of strength, and when you go to the right, it's less acidic. The minute we heated this material up to the high temperature, again, NBALO4 form, there's a significant decrease in surface area, and notice now we did not see any acidity in the high pKa range, and then there's a shift in the product distribution, and whatever acidity we have left actually are now of a very weak type. In fact, this is probably the best sample we have in terms of it resistant to thermal treatment, because in this sample we actually have more alumina than niobium, and stoichiometry will tell you that after the formation of the NBALO4 compound, you will still have some alumina left, and I think we are picking up some residual weak acid sites on the alumina which has phase separates from the compound. To back up, when we look at the mixed oxide, the other 2 compositions, we have detected no acidity after the calcination. Now, in an attempt to stabilize this material then, we have done something that's very similar to what you heard in the previous talk. I guess maybe that's why I was called on to answer the question. I don't know if I can do that, but I try. The strategy is very simple. Is if indeed the acidity arises from niobium-alumina interaction, and if the surface phenomena, you can just basically peel off the skin of that material. Well, by that I mean you're going to try to prepare a mixed niobium alumina oxide of 1 monolayer thickness, but you want to stabilize the material, and the one way to do it is simply to anchor it onto a high surface area substrate, in this case silica, thus producing a silica-supported niobium-alumina mixed oxide, or which we will refer to as a surface oxide. The recipe we use the following. The supply is a Davison 952 silica. The precursors are 2 alkoxides, in this case niobium methoxide and aluminum s-butoxide. Our experience with alkoxide impregnation, and in this case cold impregnation, is that the anchoring of the precursor to the support is facilitated by the interaction between the alkoxide and the surface hydroxyl group. So yes, the bonding is quite strong. In fact, so strong that it stabilizes the oxides from crystallization under heat treatment. In order to mimic the bulk mixed oxide, we have, from stoichiometric calculations, prepared 3 surface oxides. In this case, just to remind us that we are working with the supported oxides and not the mixed oxides, we changed the notations on you. So a niobium/alumina 1:1 means that we have now this species supported on silica, but equal mole ratio in the 2 constituent oxides. As prepared, again, we did the same 2 temperature treatment to these supported oxides. And after the low temperature heating, again, it's X-ray amorphous, which is fine. You would expect that. But now, as we ramp it up to 1000 degrees C, notice that before, when we had the bulk mixed oxide, we had the formation of the NBALO4 compound. Now we didn't see it. At the same time, the underlying silica is stabilizing the surface oxide in the sense that the loss in surface area is no longer as severe. Right now, it's not quite even a factor of 2. From the acidic viewpoint, the solid bar is the acid site distribution over the pKa ranges shown before and after calcination. And as you can see, we actually now have retained some very strong acid sites on the surface oxide, which was gone before. Granted, there is some differences between the absorption, between the base, the absorption of the base. I just broke the bond. Between and after the calcination, but the message is we retain quite a bit of acidity of this material. Now, if you compare this acid site distribution with that of the bulk mixed oxide of the same composition, there are differences. Okay? In a sense, it's not surprising because now you introduce the third component into the system. So on top of the interactions between the niobium and alumina, now both of them are interacting with silica support. A more important question is how do we know that by the co-impregnation we actually have built in the niobium-alumina interaction? In fact, one possibility is we are seeing nothing more than a physical mixture of niobium interacting on silica and alumina interacting on silica. To test that, what we have done was to prepare the two samples shown on the two sides and then characterize them. And the premise here is if the supported oxide is a simple physical mixture of the two, then we will have a simple additive effect. Well, we did not see that. I'm now showing you the results for the niobium alumina 1-to-1 sample, which is shown in the shaded bars, and then the solid bars correspond to the precursor to that, which is the niobium on silica alone, and then the open bars are therefore alumina on silica alone. And as you can see, if it's just a physical mixture, then all these things will show up of the same height. They do not. In fact, if I point your attention to the weakest pKa range here, you can see the niobium alone is more acidic than the one on the two mixed on the surface oxide. And for those of you who think that these data are too close to call, my last slide show you that we can pick up the same thing in butene isomerization. The solid line is the supported 1-to-1 oxide before and after calcination. As you can see, again, it's very stable with respect to its ability to catalyze this reaction. If we look at the bottom line, which is the selectivity shown as the ratio of cis-trans to butene ratio, then if we have niobium alone, that after calcination, we saw a significant decrease in the selectivity, which again is not picked up in the surface mixed oxide. These results taken collectively suggest that the niobium is not free to do whatever it does on silica alone, and we can draw from that that we are in that building a niobium-alumina interaction sitting on the silica substrate. To give you a one-sentence summary, then I think we are encouraged by these preliminary results into believing that the drafting of a binary oxide onto a third oxide, which provides a so high surface area for stabilization, is a viable and promising way of building new oxides of interesting acidic properties. Thank you for your attention.
Any other questions?
Have you tried making any of these materials from a non-methoxide, non-alkoxide route, say using a nitrate salt or an oxalate or something along those lines?
Which materials, the bulk materials or the surface materials?
The surface materials.
For the surface material, no. And the reason we stuck with the alkoxide route is because we want to give the two components the best chance they could have to interact with each other. And when you put the two alkoxide precursors in solution,
right.
So we basically try to build in that linkage in the solution prior to the impregnation. If you switch the precursor to one considering nitrate, which is exactly what we use in the bulk oxide, I don't think you give it as good a chance. That's basically we did it.
You form any niobium aluminates in this system?
What do you mean by many?
Do you form any forms?
Okay. Our indirect evidence is the lack of an X-ray peak identifiable to the NDAL04. Now, as you well know, if such species do exist, but they exist in small particles, we would not have been able to pick it up. But for the niobium on silica alone, we have done other work convincing us that the silica-niobium interaction is sufficiently strong to stabilize the subsequent crystallization of the supporting oxide. So I cannot rule out their presence, but they either have to be very small or they are not there. But again, I want to remind you that the acidity doesn't change at all before and after the high temperature calcination.
A quick question.
Have you looked at impregnating the niobium oxide on a preformed alumina instead of co-precipitating?
No, but we have looked at the niobium on silica, basically with the idea what your question is getting at is what acidities can one expect from building linkages from those two constituent cations.
Right.
It's a good suggestion, but I don't think we have done that. Actually, we have done some of that, but I don't remember the results.
Don't ask the next people.
Measuring that the enhancement of the gas phase reaction due to the presence of this catalyst. Essentially, just to summarize what I just said in word here in the graph here, we can detect, we try to detect the post-catalytic volume reaction by varying this volume. The two variations that we have will be there's no volume at all, and the other is there is some volume behind the catalyst. We look for any effect. If the reaction is totally on the catalyst, then by changing this volume, there will be no change in the activity or selectivity that we detect at the outlet of the reactor. However, if there is some desorption of reactive species from the gas phase, from the surface into the gas phase, then there will be a change in the activity and selectivity which we'll be looking for. To be sure that when we are looking at the particular reaction that we want, we have to do a series of 5 different experiments. First of all, this is a control experiment in which we put just the catalyst in the reactor, and the rest of the reactor is filled with the quartz chips, which I said is a quencher. This then will give us the reactivity due to the catalyst alone. And then we take off all the quencher in the volume there, the 1 inch volume, and take off the catalyst and find out what is the reaction due to the gas phase alone. Then we'll put the catalyst there with the empty volume, and we can put the feed either from the empty volume side, then what we detect at the outlet of the reactor will be the reaction due to the gas phase and due to the catalyst separately. Then we put the feed from the catalyst side. This then will give us the reaction due to the catalyst, due to the volume itself, and due to whatever enhancement by the desorption of gas phase product. And finally, to be sure that any changes between number 3 and number 4 is due to desorption of reactive intermediates from the surface, we put a quencher right here, so that any free radicals perhaps that's dissolved will be quenched and will not cause any further enhancement of the reaction in the gas phase. This is because there is a possibility that the catalyst would produce some stable products such as alkenes and dienes, which would cause a different set of reaction in the gas phase here, different from those that we detect in the other control experiments. The results are shown in the next slide here. This is one particular set of experiment. The experimental conditions are that we use a catalyst that contains 19% vanadium oxide or magnesium oxide. Actually, it's a mixed oxide catalyst. We run it at about 570 degrees Celsius. And the propane to oxygen ratio was 4:8, and this is the standard condition that we use. When we use the catalyst alone, so that there is no gas phase reaction, the conversion was about 14%. With the reactor alone, without any catalyst, under these conditions, the conversion is about 8%. If we put the feed from the empty volume side, so that there is a reaction first, which then go onto the catalyst and cause and then the catalyst cause another series of reaction, the overall conversion is about 22.9%, which is within experimental error is a simple sum of these two. If we have the feed coming from the catalyst side, we find that the overall conversion now is increased to about 28-29%. Finally, if we put a quencher, the quartz wool, right behind the catalyst and run the reaction, the conversion now has dropped back to about 22 to 23%. In essence, we do see an enhancement of the overall reaction due to the presence of a catalyst in front of a gas phase volume. There is then an enhancement due to some desorption of some reactive species, which is not stable, which can be removed essentially by the quencher if it is immediately after the catalyst. And this reactive species then would cause enhanced reaction in the gas phase. The question then becomes, what is this species, and under what conditions will we get a large amount of the desorption of the species? We study this enhancement, which is defined as the change in the conversion that we observe divided by the conversion when there is no enhancement present. And we study this as a function of, for example, the propane to oxygen ratio, and also the amount of catalyst, which is not shown here, as well as the temperature. But at low temperature, we find out, not surprisingly, that the extent of enhancement is small, only about 20%, and the extent of enhancement increased rather substantially when we increase the temperature by about 10 degrees, 15 degrees. And also the extent of enhancement increases with increasing propane concentration in the gas phase. Now, what it all means is that this measures the amount of gas phase reaction that is initiated by the desorption of the reactive species. This may or may not indicate to us directly how much of the gas phase, how much of the reactive intermediate is desorbed from the gas phase into the gas phase. In other words, what I'm saying is that although the enhancement, let's say at this condition, increased from about 15% to 45%, or threefold increase when the temperature is increased by 15%, that does not imply that there are 3 times as many free radicals or reactive species that is dissolved into the gas phase. We find that there's a rather good correlation actually between the extent of enhancement to the ability of the empty reactor without catalyst to carry out the reaction. So essentially what we are measuring here is the ability of the gas phase reaction once initiated to be able to carry on in the gas phase by itself. Well, how do we know that this enhancement is indeed due to the gas phase? Well, one thing we can do is look at the product distribution. What I showed you earlier was simply the extended reaction, that is a conversion, but there is a lot of information that is generated from the product distribution. I show you here, let's say, these 2 particular conditions, one for the post-catalytic experiment, the other for the one when we have the catalyst, when we have the feed coming from the empty reactor volume side. Of course, you see that there is changes in the selectivity, and there is some enhancement in the conversion as well. So if we look at the change in the yield of each of the species, and compare them to the yield due to the gas phase reaction alone. This is shown here for one particular set of conditions. Let's say this is for a propane conversion of about 18-19%, and then compare them. That this is then the change in yield of the product due to the enhancement of the gas phase reaction by the catalyst. And these are the various yields. And these are then the yields due to oxidative pyrolysis in the gas phase without catalyst. And you can see that by and large, they compare very well. So indeed, our enhancement is due to a gas phase reaction that would have been initiated that could be initiated by just gas phase reaction alone. But what is this species? Well, we do not have any direct evidence for it, but by the gas phase product distribution that I show you, it seems like to us that it is a alkyl species. So as a conclusion, we find that that there is enhancement in the overall conversion due to the desorption of reactive species in the catalyst. And this enhancement increases the temperature and also the pressure of propane. We have the work that we're doing now is doing a reactor modeling, taking the rate constants of the elementary steps of gas-phase reactions and back calculate what could have been the species that is dissolved. We are looking at the possibility of RQ species dissolving, or OH dissolving, HO2 dissolving, and the preliminary result we get is suggests that about 10 to 20% of the RQ species on the surface dissolve into the gas phase to account for the data that we have. And finally, one conclusion that I do not have here is that we are also look at the possible desorption of reactive species on some other catalysts. In particular, we're looking at the vanadium phosphorus oxide catalyst, which is used for the butane oxidation of magnetic hydride. And under certain conditions, about 450 degrees Celsius, we do find evidence